I'm Professor Curtis, and this is the last lecture for the course, the lecture for Chapter 36, General Theory of Relativity. Let's get started. So, in the last lecture where we talked about Einstein's special theory of relativity, we said that 1905 was Einstein's miracle year. And this was the year in which he earned his PhD in physics. And that same year that he earned his PhD, he published 4 major papers. They were each groundbreaking in and of themselves. The fact that he did 4 at the same time is the quote-unquote miracle. The first paper he published was about the quantum theory of light, which included his explanation of the photoelectric effect. And this is where he brings out the dual nature of light, the wave-particle nature of light. And it was that explanation that earned him the 1921 Nobel Prize in Physics. His second paper was on the statistical aspects of molecular theory and what's called Brownian motion, which is the motion of molecules at the surface of a liquid. The third paper was for his special theory of relativity, which we discussed in the previous lecture. And then the last paper presented the equivalency of energy and mass in the form of his famous equation E equals mc squared. So 10 years later, in 1915, remember, it took 10 years for Einstein to realize, hey, the special theory of relativity needs to jive with Newtonian mechanics in order for the correspondence principle to hold out. And I got to get this to jive with Newton's theory of gravity. But he couldn't get the special theory of relativity to do that. So he worked 10 years on that theory to come up with something that would apply generally across the board. And it took him 10 years, but he was able to do it. And so in 1915, he presents his general theory of relativity and how he was able to reconcile Newton's theory of gravity with his own special theory of relativity. Now, at the time, nobody really understood the import of what was going on. They didn't even understand the theory that he was extending. So here we see an excerpt from the London Times, and actually this is from the New York Times, and they were getting this information from the London Times. This is interesting. Check this out. The London Times, in an editorial this morning on an explanation by Dr. Albert Einstein of his theory of relativity, confesses that it cannot follow the details and implications of the new theory with complete certainty, and points out that even Einstein himself finds no little difficulty in making their meaning clear. So even Einstein himself had trouble expressing the ideas that were engrossed in his own general theory of relativity. So if you feel like this is like, woo, way over your head, you can't understand what's going on, well, neither could anyone else, back in 1915 when the theory first came out. So it just means you're normal. Okay? So we're going to try to make sense of this anyway, so we can be abnormal in a good way. The first thing we need to understand about the general theory of relativity is that no observations made inside an enclosed chamber can determine whether the chamber is at rest or moving with constant velocity. So imagine, for instance, that you're inside a rocket ship, okay? So you're not going to be able to sense whether you're moving or at rest. You will be able to know if you're accelerating. You'll feel acceleration. But if you're moving with constant velocity, you won't feel anything, okay? And this brings us to the principle of equivalence, which states that observations made in an accelerated frame of reference are indistinguishable from observations made in a Newtonian gravitational field. Okay, so if you're in a rocket ship that's completely enclosed, okay, and the rocket ship is not accelerating, so it's either at rest or it's moving with constant velocity, then, when you're far away from gravitational influences, everything's going to be weightless. But once you apply acceleration to the rocket, now you're going to feel a sense of gravity, okay, inside the rocket ship. So let's look again at different frames of reference. if we've got a ball that's being thrown inside the rocket ship, and the ball is thrown horizontally, okay, someone outside the rocket ship is going to see that ball travel horizontally in a straight line. But if you're inside the rocket ship, you're going to see the rock follow a trajectory like we normally see if you're just like standing stationary on Earth. Okay, you're going to take a path that's bent along a parabolic trajectory. So just as we saw previously with Einstein's special theory of relativity, okay, light is going to behave the same way as this ball. The path that the ball takes is going to be different depending upon your frame of reference. And per the principle of equivalence, okay, if acceleration can deflect light, then that means that gravity has to possess that ability as well. Now, hang on a minute. Gravity can bend light? Well, according to Newtonian physics, gravitation is an interaction between masses. But light doesn't have any mass. So, how is it that gravity can bend light? Well, this is where Einstein's general theory of relativity comes to play. And he came up with two explanations for how gravity is able to bend light. The first explanation is, yes, you know, you can say light is massless, but it also has energy. And because energy is the equivalent of mass through E equals mc squared, gravity pulls on mass, that means gravity can pull on energy in the light, so gravity can pull on light. The second explanation Einstein came up with says, look, light also bends just like, matter because it travels in a space-time geometry that is bent. So if space-time is bent, then that means light is going to bend too because it's just following the surface of space-time. Now, Einstein's theory of general relativity better explains different astronomical phenomena than we witnessed. So, because it's a better explanation, we abandon Newton's idea of gravitational forces between masses and instead think of mass and light responding to its motion as a effect of the warping of space-time. So when space-time is warped, that means mass and light are going to be bent as they travel from one place to another. They're moving along the surface of the space-time. So where space-time is bent or folded, then the path or trajectory that light and mass will take as they travel will follow that same pattern. Now, here's a good example of a video. This was actually made as a demonstration for high school teachers who are teaching relativistic physics to their students. But it shows a really effective here with this apparatus that this guy put together about how bends in space-time can give us the effect of gravity. So if you think about energy as being the equivalent of mass, as you're watching these objects roll around on the surface of bent space-time, then you can more easily see how gravity is able to bend light. So let's see if we can get this video to go here, and hopefully here we go.
The explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. No, there's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less, depending on the sale. And so you put matter and it warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass,
you're right there on that.
Oh. If you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. And let's get some more here. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
Is it like a toilet flushing? Southern hemisphere?
Wow, can you do that again?
And so, it won't work then. And so I have slightly more in one hand than another, but I don't consciously do that. And you want to get them so they spread out a little when you throw it.
It's because they're colliding with each other that you...
The ones going the wrong way get eliminated, right? Now there also would have been, this is where this analogy breaks down. There's, another dimension, right? But those things that were out of the plane also, that weren't near the preferred plane, also got eliminated. And so that's kind of cool. Now my students use a PHYS simulation called My Solar System. And so they've seen all this on the computer. And when we do this during our special relativity unit, they're like, hey, it's just like the computer. That's kind of cool that a stretch sheet of Lycra models things. It's not just like it, but similar to the computer. Now, some things we've discovered using this. Also, it's just some larger marbles. Might as well put them out. But they bend space-time too, right? And so maybe, you can get one thing to orbit another. There we go.
Oh my God.
So the Earth-Moon system, maybe? And so you can see that this seam, you can't buy Lycra this big. You get it in rolls, and you have to sew it together. I've been told to use stretchy thread to sew it together. And so next time I do it, I'll do that because it pulls. And so just a little bit of thread fixes it. And so in the morning, when I first set this up, I'll have it leaning against the table. I'll be underneath fixing holes from last year. One time my principal walked in. And I hear somebody in the room, and I'm underneath. I'm in the middle of sewing it. I'm not going to pause yet. And then he's looking around for me, and he kind of knows somebody's in the room. He's, oh, there you are. He goes, what are you doing there? And I go, I'm repairing a rip in the fabric of space-time. What do you think I'm doing? How often do you get to say that? Another thing this does, you've probably seen plastic ones of these, right? The Discovery Center, Children's Discovery Museum in San Jose has one. The Exploratorium has one. Sometimes they have them at shopping malls to get you to put money in it. But one thing you can't do with those is put two masses in. And so when we went to the moon, when we first started, we sent our spaceships on what are called free return trajectories. So they would go to the moon. This is hard to get to happen. And they would come back in like a figure eight. And so that lets you show, now of course the moon's a lot smaller, but if you look at the plots of the free return trajectory back from the Apollo program, you'll see it has a figure eight sort of shape. And And so this takes a little bit of practice to be able to do the figure eights. These clamps around here, you can adjust it to make it tighter if it's not working. So Steve and I, when we set this up in the morning, we played around with it, and actually I think it was working better than it usually is. And so not easy to do. And so I go through that. One year a kid who read some stuff about the dark energy. We have our dark energy pole.
It's over there.
I happen to have an extra pole. I guess any of these would work. And so I'm just thinking, oh, dark energy, what is that? That makes everything come apart, right? And so dark energy would be that. And so stuff goes apart rather than toward it. So if you can work in dark energy anytime, right? And so I go through that spiel. Maybe it takes me 10, 15 minutes talking with the kids, just stuff they're not familiar with. And then I just let them play. And so that's where we discovered the Earth-Moon thing. Is I just let them play, and they're like, Mr. Burns, come over here and look. And they were all excited because they discovered that. I said, oh yeah, it's got it.
Wow.
And so there's, then I throw out a few other things so they can try this collected stuff over time. And put out all the marbles. So if you want to try it out, but we probably want to get back to electricity and magnetism.
But we want to play, Mr. Burns.
And so I'd say the whole thing, if you bought all the parts and everything, it's about $100. But one of my favorite days, so you're going to do it Monday, right, Steve? You didn't
Yeah.
get to it. But just, you do it once and you'll be hooked. And it will take a little bit of fooling to put it together, but I'll post the plans, and it's not a whole lot of work for.
So this is a take-apartable thing, right?
It comes apart, all the PVC pipe, wrap it with a bungee cord, stuff the lycra in that box, and I can carry the whole thing myself. This is about the right size. You can get your whole class around it pretty much. Smaller. One problem is reaching. So some of you, I think, would have trouble with that, so you get a student to do it right. One thing you got to watch, though, is some students will think to go underneath to push up, and then while they're underneath, somebody decides to put the big mass down, and they get their space-time warped. And so you just tell them you can't go under. We will get things ourselves. We don't need to do that.
Even Einstein has rules.
Yeah. And so, is general relativity in the state standards? No. Probably the crowning achievement of science, not in the state standards. Can you fit it in after the STAR test? You bet. You can find some videos. I show them a thing on gravity waves, and then we do this, and that's a day, almost a day on general relativity. But since I don't understand it myself, that's plenty. So let's go back into the room.
Okay, so here you can see a pretty good demonstration there with the space-time and how warping of space-time actually leads to effect of gravity. So now, based on the video that you just watched, I want you to go to your workbook and answer these two questions. So what effect does mass have on space-time, and what shape did the Apollo spacecraft make around the Earth and the Moon? So go ahead, stop the video, take a moment to answer these questions. When you get done, come back. We'll see how well you did. All right, let's see how well you did with this. So what effect does mass have on space-time? Well, it warps it. So notice when he puts the different masses, different size balls there on the spandex sheet, that you got warping in the spandex. That's similar to what we see in space-time. At least that's Einstein's conception of it, that you get that warping of the surface, and so it's the change in the surface there that leads to the effect of gravity. So, second question, what shape did the Apollo spacecraft make around the Earth and the Moon? And the answer to that is it made a figure 8. So you're using basically the effect of motion around the Moon to basically serve as a slingshot to propel you back to the Earth. let's consider a case where we have 3 different clocks. And so we're going to place 2 of those clocks on a spinning disk. So the disk is going to be spinning at a constantly accelerating rate. So the speed at which the disk rotates is going to keep changing. And then one of those clocks is at the center, and the other clock is at the edge. And then a third clock we're just going to leave off the disk and have it be stationary in an inertial frame of reference at rest. So from the laws of special relativity, we know that clocks number 3 and number 1 should be running at the same rate. Because even though clock number 1 is spinning, it's not really moving any distance. Okay? Not like clock 2 out on the edge, which is consistently following a path of a circle going around and around and around. But clock number 1 is essentially keeping its same position. It's just twisting itself, rotating around in that one position. So clocks number 1 and 3 should run at relatively the same rate. But clock number 2 is going to be running much more slowly. Okay, now out there at the edge of the disk, clock number 2 was under the influence of a centripetal force. Okay, that force decreases with distance from the center. So the further out we get from the center, the greater the centripetal force, and so the more time is going to be slowing down. So the principle of equivalence tells us that if we're moving along the direction in which any force acts, and gravity is a force, well, that likewise must slow time. So from this concept, we can conclude that a person who's working on the ground floor of a skyscraper will age more slowly than a twin working on the top floor. Of course, the distance is going to be very small because, relativistically speaking, the distances aren't that great, but there will be a slight difference at the rate at which a person working on the top floor is going to age with respect to someone who's on the ground floor. This leads us to the idea of gravitational redshift. Okay? As I said, the heights of skyscrapers are relatively small distances. Let's look at the distances between astronomical bodies. Okay? So the effect of gravity on time is easier to observe when we're looking at astronomical bodies. So we've seen previously that atoms will emit light at specific frequencies corresponding to frequencies at which they vibrate. This gives us the whole idea of atomic spectra. Okay? So in this sense, every atom is itself a sort of clock. And because the Earth revolves around the sun, okay, so the sun's going to be like at that clock that was at the center of the rotating disk. The Earth is like the clock that's at the far end of the disk, out there on the edge. So time is going to be slowed on the Earth and not the sun. This means the frequency will also be slowed, because remember, that's what frequency is. Frequency is the reciprocal of time. So if time is going to be slowed, that means the frequency is going to be changed as well. So an atom on the sun emitting light at a lower frequency than light that's emitted by the same element that's going to be on the Earth. And this effect is what we call gravitational redshift. So called because we're slowing down the frequency. So slower frequency means longer wavelength, and that means we're moving towards the red end of the visible spectrum. That's why it's called red shift. Because remember, red light has a longer wavelength and there's shorter frequency than light at the other end of the spectrum. Now, we talked about how this sort of aging, especially like the twin paradox, and if you're in one place versus another, the time will seem to slow down for you. And so some people have taken this idea to wonder, what can relativity do to help you live forever? Well, it turns out relativity cannot help you live forever. Okay? There's no way that you can extend the duration of your own existence. So if you're like, wanting to live forever, but, do this idea of relativity, and you find out you can't, you probably end up like Grumpy Cat saying bummer. Or some other obnoxious thing the Grumpy Cat would say. But, even though time is going to slow, it's not going to slow for you. it only slows for people that are looking from another frame of reference. So, time within your own frame of reference always stays the same. And that's why, longevity is going to be seen from other people's frame of reference, but never from your own. So relativity cannot help you live forever. Okay, once you're done with your existence, then that's pretty much it. So, yeah, relativity cannot help you to live forever. This brings us to the idea of geodesics, okay? Because what relativity does help us to understand is the way that light and mass travel through space-time. Now, space-time, as we saw with that spandex sheet in the demonstration video, is pretty much flat, except in the places where mass is concentrated. Where mass is concentrated on the surface of space-time, the mass will curve space-time. And the greater the mass, the greater the curvature. So think of it like the surface of a water bed, okay, with a heavy ball resting on it. The greater the mass, the more curvature you're going to get in space-time. So the shortest distance that we see between 2 points on a flat surface is a straight line. But when it comes to a curved surface, the shortest distance between 2 points is a curved line, known as a geodesic. You remember Fermat's principle that light is always going to travel along the path of shortest time? Well, according to Einstein's general theory of relativity, because space-time is curved, gravity is going to exist where the curves are. And all of this, you put all this together, and the conclusion you come up with is gravity bends light, because light is traveling on the surface of space-time. So, every object with mass is going to warp the space-time that surrounds it. And when an object then moves, okay, the surrounding warps in space-time are going to adjust to account for each new position of the object with each moment in time. So what you get, in a sense, are ripple effects that form gravitational waves in space-time. Now, gravitational waves will move at the speed of light, but they're so weak that we have yet to verify them experimentally. I think some people have gotten close, but we still haven't yet verified them experimentally. And so it's still just kind of an idea for right now, but or what we call a hypothesis, because we haven't yet experimentally verified it. But yeah, the idea is that gravitational waves are going to move at the speed of light. Here's another video, and this does a pretty good job of explaining the different warps that we see in space-time and how that gives us the effect of gravity, as well as its effect for bending actual light. So,
after nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the 3 dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this 4-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity.
A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now
if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is, its warps and curves in the fabric of space and time.
Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
So you can see here, I like the graphic that they get there where you're looking at bends in space-time. Then that's what gives us the effect of gravity. So with that in mind, go ahead and go to your workbook, and based on the video we just saw, answer these two questions. 1, how does Einstein's general theory of relativity explain motion due to gravity? And 2, at what speed do gravitational waves travel? So go ahead, stop the video, take a moment to work this out, and then come back and we'll see how you did. Okay, let's see how you did with this. So, first question, how does Einstein's general theory of relativity explain motion due to gravity? Well, it says that everything exists in space-time, and so curves in space-time provide the paths for motion that we observe as the effect of gravity. At what speed do gravitational waves travel? They travel at the speed of light. So Einstein's theory of general theory of relativity helps us to explain the presence of black holes. When a star expends its nuclear resources, it collapses, okay? So it doesn't lose mass, okay? Instead, what happens is the mass just gets concentrated in a much smaller space. So there's no loss of mass, but there's a huge loss in volume. And because the mass becomes more concentrated, okay, that concentration of mass causes space-time to fold in on itself. And so the gravitational forces around these folds are so great that in their immediate vicinity they attract anything, matter, energy, even light. And because they're attracting light, okay, that's why they look like they're black, because that's where black comes from. Remember black when we studied about color? Black is, things that are black absorb all wavelengths of light. So there's nothing that's reflecting back for us to see, and so that's why it looks black. So because the objects are absorbing all the light, that's what makes them black, and that's why we call these areas of concentrated mass and folded spacetime black holes. Newtonian theory does not account for black holes, but Einsteinian theory does. And so this is one more reason why we go with Einstein's theory and not Newton's. Now, keep in mind, Newton wasn't perfect, and neither were his theories. But at the time Newton extended his theories, they did help the world to understand how the universe worked. And Einstein is just another, represents another generation that has improved upon the understanding that's come before. So each time we make an improvement, okay, we're revealing imperfections in the understanding of those who came before us. But that's okay, because now, see, we've got an improved understanding. And who's to say that people who's going to come after us aren't going to improve on what Einstein did? So, we understand we understand more than what Newton understood, but somebody coming along down the road could understand more than we understand. They're going to expose the imperfections that we have in our current understanding. And so you can see that, as we keep forward and forward in time, we keep improving our understanding of the world around us. And the greater our understanding of the world around us, the greater we can appreciate the world and the universe in which we live. And that's something that makes life more worth living. So I hope that you've been able to enjoy not only this lecture, but this course. Thank you so much for watching, and we will see you in the next class period. Because, of course, you know, that's because you got your test coming up. So, yes, we will see you in class.